In this video, I'll walk through a real optical design and show how to use structured prompts using RAI to move from system requirements to a verified baseline design. RAI is often used for simple designs, but complex systems require a different approach. System design follows established engineering workflows, starting with architecture, then refining details and verifying each step. We'll start from the application and a small requirement set, reason through viable optical architectures, adapt a real starting point design, and verify the result to close the loop through requirements traceability. Along the way, I'll show the prompts I use, what RAI returns, and where applying your own judgment is essential. I'm using a space-based lightning imager as the example, a fast wide-field refractive telescope used in a geostationary weather monitoring mission to observe global lightning activity. If you'd like to learn more about this application and design, I'll leave a link in the comments. We start the design by giving RAI context, the application, and a small set of target specifications. Avoid providing every constraint up front. Early optical design is about choosing the right solution space. I begin with field of view, f-number, wavelength band, and mission needs, then add constraints as the design matures. Next, RAI generates a structured table that breaks the system into functional groups. For each group, it identifies function, allocated optical power, and key constraints, matching standard requirements allocation. A short list of design forms is then recommended based on how well each meets the system needs. From this reasoning, several candidate design forms are proposed. Each represents a viable architecture within the defined trade space. You can inspect each library file using the launch icon, while RAI checks alignment with the original architectural intent using the same criteria. Each candidate is then scored and checked for compliance against metadata and file content. Based on this analysis, clear recommendations are provided for the designs most aligned with the original requirements. Based on this review, the Petzval f1.4 with a 14-degree field of view is selected as the starting point. Next, RAI performs an architectural review of the selected design. It evaluates every element, surface, material, and airspace against the original architectural requirements. Gaps in the design are flagged, and RAI proposes specific changes. In this design, the recommendation are to add a field flattener, relocate the stop, adjust airspaces, scale the design to the target focal length. Review these recommendations and approve or modify them before moving to the next step. At this point, a baseline design is created from the starting point designs along with the approved changes. RAI provides a design summary to serve a record of the design process up to this point. Next, the design is verified. RAI generates a compliance checklist for architecture, element count, surface shapes, spacing, and power distribution, and shows the reasoning behind each check. This keeps the verification reviewable. Every finding and conclusion can be inspected, and adjustments made to the design before moving forward. In this design, verification surfaces a real issue. Here, the Petzval air gap is too short. RAI explains why this matters and suggests a correction. Review the details, approve the change, and move to the next step. With the overall design in good shape, the design is revised toward an all-fused silica, plus one flint element, instead of doing a simple material replacement. I ask RAI to propose a plan. The first pass exposes a problem with this prompt. The material constraint is not precise enough. To refine it, RAI is asked to critique its reasoning. This iteration uncovers a better solution. The last step in this workflow is to run a full geometry check to confirm the design supports real manufacturing constraints. This answers a simple question: can the design be built? RAI checks thicknesses, air gaps, interference, and stop placement, and flags anything physically inconsistent. If there is an issue, we fix it and recheck before moving on. With optimization complete, we're ready to generate the ray trace and produce a 2D layout of the system. Because AI models like RAI operate within a finite context window, it's often best to start a new chat session for detailed simulation tasks. This keeps the design history clean and ensures the system has enough memory available to trace rays accurately and handle larger data structures. At this stage, we've transitioned from concept to engineering, with a complete traceable design that's ready for downstream validation and refinement. This demo shows how structured prompts fit into established optical engineering workflows and support early system-level decisions. Thanks for watching. If you have questions or would like a copy of the prompts used in this demo, feel free to reach out.